Hi guys, this video is going to cover the area review warm-up and then the notes for 11.4, which is geometric probability. So we'll start with the warm-up. Find the area of each figure. Number 1 says a triangle with base 6.3 centimeters and a corresponding height of 9.8 centimeters. So hopefully remember that the area of a triangle is equal to 1/2 base times height. So this would be 1/2 6.3 times 9.8. Now you can either multiply 6.3 and 9.8, divide it by 2, or you could divide either one of those by 2. So because 9.8 is even, if we did a half of that, it'd be 4.9, and then I'd be multiplying 4.9 times 6.3. So 6.3 times 4.9, 9 times 3 is 27, 6 times 9 is 54, plus 2, that's 56. 4 times 3, we'll put the 0, 4 times 3 is 12. And 6 times 4 is 24, plus the 1, that's 25. Add those together. There's 2 digits behind the decimal, so the answer here would be 30.87 centimeters squared. Looking at number 2, it says parallelogram with a base of 4√3 and corresponding height 3√5. Again, area for a parallelogram, base times height this time. So this would be 4√3 times 3√5. Remember, with square roots, we're going to multiply what's on the outside together. So 3 times 4 is 12. And then square root 3 and square root 4 would be square root 15, which doesn't break down at all. So that would be that, units squared. Number 3 is a rhombus with diagonals 6 and 8. So diagonals are what you need for a rhombus. The area of a rhombus is 1/2 diagonal 1 times diagonal 2. So this would be 1/2 6 times 8. And you could either do the half of the 48 or half of 6, which is 3 times 8. Either way, you get 24. Again, no units this time, so units squared. Number 4 says an isosceles triangle with sides 12, 12, and 10. So we're going to draw that one down here. I need height here because I have the base, but I have the 2 legs instead of the height. So what happens when we draw the altitude to the base of an isosceles triangle is it cuts it into 2 congruent parts. And then if I want to find the height of this triangle, I can use either the right side or the left side, but I can use Pythagorean Theorem. So if you remember, there's a triple that it's 5 and 12, but that's 5, 12, 13, where 13 is the hypotenuse. So we can't use that here. We do 5 squared plus h squared equals 12 squared. 25 plus h squared would equal 144. Subtract the 25. And I get h equals the square root of 119. That's the height of this triangle. So if I want to find the area, it's 1/2 the base, which is 10, times the height, square root 119. 1/2 of 10 is 5, so it's 5 root 119. Units squared. And then number 5 says an equilateral triangle with sides equal to 9. So this time we want to look at equilateral. It's still 1/2 base times height, or it's 1/2 ANS. So you could use either one. If I know the side lengths are 9, then I can draw an equilateral triangle where it'd be 9, 9, and 9. Because it's equilateral, if I draw the altitude, it's actually going to cut this 60-degree angle into 2 30s. And this would be 60 and 60. So if opposite the 30 is 4.5, because that 9 is divided into 2 congruent parts. And let me zoom in on that. That would mean this is your A, this is your A root 3, and this is your 2A. That makes the height of this triangle 4.5 root 3. So the area would be 1/2 the base, which is 9, times the height, which is 4.5 root 3. So I can do 1/2 times 9, 4.5, or I could have done 4.5 times 9 and then cut it in half. 4.5 times 4.5 is 25. That's 22, 20, and 18. 2 digits behind it. So my area would be 20.25 square root 3. And again, no units this time, so it would be units squared. If you wanted to practice the area of a regular polygon, you could have also used your apothem here. This side length would have been 4.5. Had I done 360 divided by 3, this entire angle would have been 120. Cut it into 2 smaller parts, and now you've got a 60, 30, 90 triangle this way. So the number of sides is 3. The length of each side is 9 because it'd be the whole side. What we need is the apothem. So this time, this is A root 3, this is 2A. So if 4.5 equals A root 3, I would divide both sides by root 3, rationalize, and there's my A. So when I plug it in, area equals 1/2 A, which is 4.5 root 3 over 3, N, which is 3, S, which is 9. The easiest way to start this is these 3's cancel. And then I've got 1/2 4.5 root 3 times 9. So we're exactly where we were before, where I can do 1/2 of 9, 4.5 times 4.5 times root 3, which gives you that 20.25 root 3. So either way you approach an equilateral triangle, you'll end up with the same answer. Okay, so the last section that we were going to cover before your test is 11.4. So as of now, we'll kind of keep that the same, just postpone the test, but we'll wait and see as we get closer to what's happening. 11.4 is geometric probability. So we talk about probability. It's the likelihood that an event will occur. It is a number between 0 and 1, and it can be written as a fraction, a decimal, or a percent. The probability of an event A is written as P of A. So the closer to 0 it is, the harder it is for that probability, or the less odds there is. If it is 0, it's actually impossible. It's like saying, what would happen if I flipped a coin? What are the chances I could get? Roll a 2. So obviously we can't roll a 2 if we're flipping a coin, or vice versa. If I wanted to roll a die and get a tails, that's obviously not going to happen. So those would be impossible events. P equals 1 is a certain event, or like 100%. You know for sure it's going to happen. And then everywhere in between, the closer it is to 0, the less likely it is for that to happen. The geometric probability is a ratio that involves a geometric measure such as length or area. So we'll find the probability that we're going to land on a certain segment, or a probability that we're going to land in a certain shape, that kind of thing. So we'll start with the length, probability and length. If AB is a segment that contains segment CD, or let AB, be a segment that contains segment CD, if point K on AB is chosen at random, then the probability that it's on CD is the ratio of the length of CD to the length of AB. So this is a lot of words to say. Basically, we want to put what we're aiming for over the whole thing. So if I had drawn this on the board and I had asked somebody to go to the board and put point K anywhere on AB, what we're looking at here is what's the likelihood that person would put it between CD. And to find that, we would get the length of CD and we would put it over the length of AB. So these will be simplified fractions. We'll set them up as fractions and then reduce them as much as we can. Probability and area. Let's say now we're dealing with shapes. Let J be a region that contains region N. So in this diagram, J is the bigger object. M is the smaller one. we want to know the probability that a point, again, any point that's chosen on J, would fall within M. And the way we find this is doing the area of what you're aiming for over the area of the whole shape. Sometimes they're obscure shapes like this. Sometimes they're going to be rectangles or triangles or any of the shapes that we already have. You're going to want to find the area of this, what you're aiming for, over the area of the whole thing. And then again, we'll reduce it as much as possible. Here's the first example. Suppose point P on segment AF is picked at random. What's the probability P is on segment CF? Given AB is equal to BC is equal to CD, DE, and EF. So we actually don't have measurements here. We could give these any kind of value we want as long as they're all consistent. So let's just say that this is 1 unit, this would be 1 unit, this would be 1 unit, this would be 1, and this would be 1. If I want to know the probability that it's on CF, I'm going to find the length of CF, and I'm going to put it over the length of the entire segment, which is AF. So if we start with AF, that's 1, 2, 3, 4, 5 units long. And then we want to look at just CF. So from C to F would be 1, 2, 3 units long. So the probability that P is located on CF would be 3 out of 5, or 0.6, or 60%, depending on how the answer is asked. If it's not asked, then you'll leave it as that simplified fraction. So let's say I hadn't chosen 1 for each of these segments. Again, as long as we were consistent. Let's say I said each of these was 2 units long. It would have been 2, 4, 6, 8, 10. So the entire segment would be 10. And then C to F would be 2, 4, 6. So 6 to 10 would still result in 3 to 5, which is still 0.6, which is still 60%. So as long as you made them each the same length, you would have gotten the same answer once you reduced it. Okay, at a carnival game, dishes are positioned on the table so they don't overlap. You win a prize if you throw a nickel that lands on a dish. If the area of the table is 1.5 meters and the combined area of the dishes is 1.5 meters squared, and the combined area of the dishes is 1 meter squared, what's the probability that the nickel will not land on a dish? So for these, you probably want some sort of visual. I know that's how it's easiest for me. So I'm going to draw a table. So I know it's a rectangular table. And then it has dishes on that table. So it just says that the table has dishes and they don't overlap. So it could be a total of 3 big dishes, 2 big dishes, or they could be a bunch of little dishes on that table. All we know is they don't overlap. And then what we also know is that the area of the entire table, so the entire thing, is 1.5 meters squared. And the combined area of all the dishes, so if I had taken and I had added the area of all these dishes, again, whether it be 2 dishes or 3 dishes, whatever it might be, however you set it up, the combined area of all of those is 1 meter. So if I was aiming for the dishes and I wanted to know what's the probability, I would put that 1 meter over the 1.5 meters squared and squared. But it's saying what's the probability it's not going to land on the dish, so I want to know all the other area. So I want to know 1.5 minus 1 over 1.5, or 0.5 over 1.5. Now you can't leave the decimal within the fraction, so I'm going to move this over once and this over once, and I get 5 over 15, which is 1/3. That would be approximately 0.3 repeated, or actually not approximately, it would be 3 repeated, or approximately 33.3%. Because all of the other ones are rounded, this is your best answer, 1/3. Now they both have the meters in them, so you don't need to keep it, which is why we've eliminated it. But again, be really careful on the wording. This time it said, what's the probability of it not landing on a dish? So I wanted to know what the area was outside the dish. Okay, last question says a dart lands at a random point on a square dartboard shown. What's the probability that the dart is within the outer circle and then within the bullseye? Use 3.14 as pi. So first thing we're going to do is answer the first question, the outer circle. Actually, first thing to do would be find the area of the big shape, the entire whole square here, which would be 10 times 10 or 100. So both of these are going to go over 100. The first one is probability that the dart is within the outer circle. So I want to know what it would be like to be in just the outer circle, which means I'm going to find the area of the big circle and I'm going to subtract from it the area of the small circle. So to do that, the whole circle would be 4 plus 1, which is 5. So the big circle is 25 pi because that's 5 squared times pi. Then I'm going to subtract from it the area of the inside circle, which would be 1 squared times pi or 1 pi or pi, which means this is 24 pi. So now I would do 24 pi over 100, and then I'm going to reduce this. So 4 goes into 24, 6 times, 4 goes into 100, 25 times, and I get 6 pi over 25. Now, if it had said to leave that in terms of pi, which most likely would be something you'd see on your test, you would leave it that way. But because this said use 3.14 as pi, we're going to take that 6 and multiply it times 3.14. Two digits behind the decimal place, and that's going to go over 25. And then I'd need to divide that because, again, you don't want to put the decimals inside the fractions. So you can either move this twice and add on 2 zeros and then reduce it. So this would be 942 over 1250, which again we can reduce. That'd be 471 over 625. Or you can take that number, that 19 or the 1884, and divide it by 2500. So again, it kind of depends on what the directions would say. If it wants you to keep it as an exact fraction, you would leave it as 471 over 625. If it said to round it, you would make that 0.7536, which rounds to 0.75. So it all depends on what the directions say on how you'll answer this question. On the homework, we try to be specific and say what to do. Same thing for the practice and the review. So that was only the left side of that, which was within the outer circle. The second thing says within the bullseye. So we know the bullseye's area is just 1 squared times pi or pi. And again, if it's kept in terms of pi, we leave it like that. If you want to use 3.14 over 100, you'd have to move your decimal places. 314 over, add on 2 zeros. And then simplify that. So again, if it said to keep it in terms of an exact decimal, you could divide that by 2. That's 157 over 5,000. And if it said to round it to the nearest place, or the nearest hundredth, let's say, it'd be 0.0314 or 0.03. So probably, again, when we take this test, you would leave these answers in terms of pi, like pi over 100 or 6 pi over 25. If the homework does say to round it or use 3.14 for your pi, then you know you're going to continue on. So that wraps up 11.4. please, before tomorrow morning, so the next assignment that you have due is the 11-4 homework. And then you'll see 2 more assignments, one with the review from the book. And one with an interactive view or interactive review on Canvas. And then you get to enjoy your spring break. So good luck with the rest of this week. Remember to keep on top of those assignments, and then I'll be releasing the solutions as the days pass. Please make sure that you reach out if you have any questions. Just shoot me a message in Canvas or an email with any questions or concern, and stay healthy, guys.